Welcome all to lecture 13. So, before starting about today's lecture, which is on subsurface wave methods, I would like to highlight here, like in lecture 10 and 11 we discussed about seismic reflection method, and in earlier methods we discussed about seismic reflection methods, seismic refraction methods, and while discussing about those methods, when we particularly were discussing about creating a shock wave, and based on the response of the ground against that shock wave, which will be recorded at over a range of geophones, we will be able to interpret the subsurface properties. So, when we were discussing about different types of wave, we discussed about, so you create a shock, it can be artificial, like in terms of traffic movement, explosion, traffic, explosion, machine operation, etc. And there can be natural resources or other sources which you are actually not creating. Again, here also you can have maybe like earthquake, etc. As a result of which, as a result of these shock waves, primarily two kinds of wave will be generated. So, one we called as body waves, because these travel within the body of the earth and can be assessed at different recording stations, particularly when you are talking about earthquakes, it can be recorded at global recording stations. So, body waves, further you can divide it as P wave, that is primary wave, or compressional wave, it is called as primary because these are the first wave which will arrive at a recording station because of any kind of shock, and it is again called as compression wave or longitudinal wave because it is causing some kind of compression or rarefaction along the direction of the wave propagation. The next one we discussed was S wave, that is called as shear wave or secondary wave, because the passage of these waves through the earth medium cause shearing in the direction perpendicular to the wave propagation. So, there will be shear waves or secondary waves. So, in order to based on the kind of shock we are generating, we will be recording the resistance offered by the material, that is the subsurface medium, against P wave if you are interpreting the results in terms of P wave. Secondly, S wave if you are interpreting the results in terms of shear waves. Now, in addition to this, we also discussed there are surface waves, primarily Rayleigh wave, which cause some kind of elliptical motion, just like ripples in water. So, particle will undergo some kind of elliptical motion like this, and then Love wave, which will cause translational motion. So, when we discuss about seismic reflection method, we more focused on primary waves, that is P wave interpretation, and then based on Poisson's ratio of the material through which the waves are passing. Once you know the P wave velocity, you can classify the material and also you can determine how much will be the shear wave velocity. But issue here is, like particularly in case of one thing, like most of the time whenever we are interpreting the subsurface medium, we are interested to find out shear wave velocity, because that is going to give you indication of shear strength of the material, which is more important as far as particularly for seismic scenarios. Shear velocity directly you can quantify for medium identification, but issue here is medium identification. but issue with body wave is like near the surface of ground body waves have very low signal to noise ratio. Or we call it as S/n. Now, we call it as signal, that is the vibration you are detecting based on the source, and noise we call it other resource, I mean source which is known to you, and then you can have noise like vibration from other sources which are there in the surrounding region, sources from the surroundings. So, when we are interested to interpret subsurface medium, particularly near surface, near the surface of the ground, that is shallower medium, maybe top 50 meter depth, we are more interested to find out the subsurface medium type. If we go with primary wave or body wave based interpretation, mostly you will end up in low signal to noise ratio. That is how you whenever you do the analysis, you will face problem. But so the another alternate which can be found here is, we can go with again subsurface interpretation. But based on surface waves. In that further we can call it as Rayleigh wave, which contains a major portion of energy generated from the shock. So, the beauty or the advantage is Rayleigh wave is like these are low frequency, relatively low shear low velocity of propagation in comparison to primary wave, but with significantly high higher amplitude, or in comparison to direct measurement of shear wave, the signal to noise ratio will be higher signal to noise ratio. Further, it has been observed, so these Rayleigh waves, because these are causing elliptical motion or some kind of a rolling effect, these are also called as ground rolls, because once Rayleigh waves are passing through a medium, it is causing some kind of roll. It's very much similar to something which is rolling on the surface. So, it is also called as ground rolls. So, in many literature you often find surface wave methods to be discussed as methods which are based on the ground rolls. Now, another thing which I would like to highlight, see, we are interested in finding out the subsurface material characteristics. I told, like particularly when we go for seismic scenarios, we are more interested to find out the in situ shear strength of the material or classification of the material in some parameter which is an indication of shear strength of the material. So, we precisely go for shear wave velocity, but here in case of surface wave analysis, since we are not going for directly shear wave velocity, but we can actually estimate the shear wave velocity considering at low strain, because whenever some kind of shock will be generated, whenever the wave will be passing through the medium, it is inducing some kind of strain in the material, and at low strain or lesser, it has been observed that the value of VR, that is Rayleigh wave velocity can be approximated to 0.9194 times Vs. This is called as shear wave velocity. So, both when we are talking about shear wave velocity, it will be for a particular medium. So, if you are having stratification, each medium or each layer will have different shear wave velocity, and if the strain based on which you are measuring Rayleigh wave velocity, if it is particularly on lower side as given here, you will be able to find out Rayleigh wave velocity, and based on this correlation you will be able to determine the value of the shear wave velocity, which is particularly for your interest. And if you recall, based on your shear wave velocity or based on your primary wave velocity, you will get an idea about what kind of medium is existing below the ground surface, because all these methods, when we go for geophysical methods or seismic methods in particular, those do not get any sample and often are classified as non-destructive methods. So, when it is non-destructive, you are not getting a sample, you have to classify based on some parameter which is an indication of what kind of medium is available at the ground surface or beneath the ground surface. Now, another thing, this value of Rayleigh wave velocity is a function of Poisson's ratio of the medium. So, if I classify here, so Vp, Vr over Vs, and this one is Poisson's ratio. So, over a large range of Poisson's ratio it has been observed, like if we consider 1, 2, 3, 4, 5. So, it has been observed, and here again I can measure different value of Poisson's ratio 0.5, 0.4, 0.3, 0.2, 0.1. So, it has been observed like up to a value of, if I consider here as shear wave velocity of the medium, that is this line is indicating Vs. So, your Rayleigh wave velocity up to 0.2, 0.25 Poisson's ratio will be like this, after that it will be like this. So, this is like Rayleigh wave velocity, which is approximately equal to your shear wave velocity depending upon strain and again depending upon how much is the Poisson's ratio. If you same way, if you see the value of primary wave velocity, you will see it will increase like this. This is called as your P wave velocity. So, unless you know the subsurface medium, it will be difficult to get an idea about Poisson's ratio. So, that is why it will be always better if we are interpreting the subsurface medium in terms of Rayleigh wave velocity, because almost throughout the range of this will come till here, nothing will be there, because beyond 0.5 it will not be possible. So, this is going to give you Vr, you can approximately consider Vr can be used. So, I discussed like what is the advantage if you go for surface wave analysis. It will be the record will be containing higher signal to noise ratio, because the amplitude of surface wave particularly near the surface will be significantly higher in comparison to if you directly use your primary wave or shear wave velocity. So, when we go for surface wave method, we are interested to find out Vr value. So, based on your field record you will be determining your Rayleigh wave velocity. It can be further used, to estimate shear wave velocity. Again, based on your shear wave velocity you can classify your subsurface medium. That is the objective of your site investigation program. You have to classify what kind of medium is there, what are the different thicknesses of the medium are there. So, based on your Vs value, suppose Vs value is 180 meter per second, I can classify the material as medium as soft medium. Similarly, if it is greater than 1500 meter per second, I can call it as weathered rock or very stiff soil. So, that is how standard classification charts are also given based on Vs value, where you can classify your subsurface medium. In addition to this, it is going to give you your surface wave method, I mean the Rayleigh wave velocity profile, or equivalent to that the shear wave velocity profile, like at different depths. So, based on this classification of this different material based on the range of shear wave velocity, you will be able to identify what are the thickness of maybe soft medium, what are the thickness of weathered rock layers, and so on and so forth. Now, one important observation, one important characteristics which we are going to discuss here is dispersion. Dispersion of wave. So, what dispersion says in a homogeneous, first of all, it is like based on your shock which you are causing at your source of vibration, that will be having different frequencies. Like there can be lower frequency, that can be higher frequency also. If I say maybe one shock here, equivalent to that, if I determine how much will be the frequency content here, maybe it gave you some value like this. So, this is like frequency and this is the amplitude. You can get based on your fast Fourier transformation how much is the frequency content. So, this is going to give you what is the frequency content of that wave and what is the amplitude of each frequency content here. Now, what happens? So, this is like this is at the source, I can say here, but what happens particularly when your medium is dispersive, in case of homogeneous medium, like the medium characteristics are not changing throughout the volume of the subsurface material, what will happen? The frequency content will not change, or what I mean to say, so there will be like different frequency waves, different frequency, I can call it as maybe harmonic waves, different frequency, but harmonic waves will be there. So, if you are going with if a source which is creating summation of different frequency harmonic wave, that is the kind of random vibration here, if you are generating it and if you are allowing it to pass through a homogeneous medium, what will happen? The frequency content of the wave will not change, that is each wave or each frequency content will travel at same velocity. So, when each frequency content is going to travel at same velocity between your source and site, which may be at certain distance away, if you put two receivers here or two geophones which can detect, so the kind of vibration you are seeing at the source, same thing you will be receiving at the site also, because the frequency content of each harmonic motion will remain same, like the frequency of the propagation velocity of each frequency content of wave will remain same. So, same thing will be same, I can call it as wave content at the site. So, it is not going to change. Now, this characteristic is particularly in case of homogeneous medium. So, the medium in which all frequencies travel at same velocity, such a medium is called as, again I am talking in terms of velocity, in terms of means Rayleigh wave velocity, because we highlighted the advantage of Rayleigh waves. So, now onward I will be discussing about the advantages and interpretation of Rayleigh waves. So, this is like in general like surface wave. So, same velocity, the medium is called as non-dispersive medium. So, it is not going to change the frequency content of wave, it is not going to change the propagation velocity of each frequency content of the wave. It is called as non-dispersive medium. However, on the other hand, this is about non-dispersive. On the other hand, there can be a possibility that your soil is having heterogeneous medium. We will go in further detail here, like soil layer 1, soil layer 2 and so on, you will be having. So, these are adding some kind of heterogeneity, and even within one soil layer, maybe the soil property is not constant throughout the depth, because here I am classifying based on average resistance offered by the material in terms against the shock. So, this is called as a heterogeneous medium. What will happen here in this medium, if you put a source here and a receiver here, the frequency content at the source and receiver will be different, that is frequency content, or I can say like Fourier spectra at source and receiver, because finally you will be interpreting the results received on the receiver. At receiver will be different, which is an indication of different frequencies of waves or wave content, I can say, travelling at different velocities. So, this characteristic is called as dispersion, which is giving an indication like different frequencies are travelling at different velocities, dispersion. And why it is happening? Because medium is heterogeneous. So, dispersion, I mean when the same frequency content is propagating from one medium to another medium, the frequency of the velocity of at a particular frequency wave content to travel may increase, may decrease depending upon the physical properties of second layer, third layer and so on and so forth. And accordingly, this will affect your time of arrival of each frequency content at your receiver. So, because the time of arrival of each frequency content is changing, you can call it is like different frequencies are travelling at different velocities. This characteristic is called as dispersive characteristic, and it is indication of the medium is not homogeneous, or moreover it is like heterogeneous medium. So, this characteristic is against Rayleigh wave, and it is an indication of heterogeneity present in the medium. So, in surface wave analysis or in precisely Rayleigh wave analysis, when we go for, we are interested to understand the dispersive characteristics of the medium which has been identified, which has been seen based on source frequency content and based on receiver frequency content. And if we are able to interpret this dispersive characteristic, we are interested to find out the corresponding medium which is inducing this kind of dispersive characteristic to your shock content. So, when we go for, again let me tell you, medium is heterogeneous as a result of which it is causing dispersion in wave content between the source and the site and the receiver. So, in surface wave analysis, if we can determine dispersion characteristics of the medium, we will be able to approximate, or we will be able to find, this will lead to finding out the possible stratifications which is leading to above heterogeneity or above dispersion. So, heterogeneity is causing dispersion. Once we know that dispersion, we are trying to find out what heterogeneities can cause this dispersion, rather than dispersion to heterogeneity, particularly when we go for surface wave analysis. That is why we go for inversion analysis, that we are going to explain later. So, inverse analysis is going to give you what equivalent characteristics of ground can give you these dispersive characteristics. So, if we consider that the strength properties, shear strength properties, or I would say in general like stiffness, increases with depth, what will happen? This will lead to lower frequency content which will be corresponding to larger wavelengths that will be propagating deeper depths, deeper layers, having higher stiffness, as a result of which what will happen to the propagation velocity? The velocity of Rayleigh wave propagation of Rayleigh wave will increase. Same will be applicable to all the frequency contents. So, if you plot this thing for a particular medium, you can call it is, so when we go for collective understanding of dispersion, we call it as dispersion curve, which is going to give you how the frequency content or how the velocity of each frequency content has been governed by particular stratification which is available at the site. So, you can get maybe something like this. which is going to give you. So, on this we will be having the phase velocity, and on this side, that is on x axis, you will be having your frequency content. Now, it is going to give you, corresponding to this phase velocity, what is the on an average the propagation of different on an average the propagation of this frequency content. This is going to give you an indication corresponding to this frequency, what will be the wavelength, and corresponding to that wavelength what depth you are actually trying to interpret on an average. So, the overall is going to give you, because if you go for point number 1, it will be having some component from shallower depth, some component from deeper depth. If you are going for higher frequency content, this will be more dominated by the content or the content of modification coming from shallower depth. So, if I go here, we can call it as deeper depth dominated. This will be like shallower depth dominated, which can be understood from corresponding to this what will be considering the same like for each medium, if you consider same value of shear velocity or Rayleigh velocity, it will be, so higher frequency content will be indicating the lower wavelength, or that is shallower depth dominating, and so on and so forth. So, this is called as dispersion curve, which is the characteristic of medium heterogeneity. So, in surface wave analysis, we are interested, again repeatedly I am telling, in surface wave analysis, based on the dispersive characteristics of the medium, we are interested to find out what is the medium heterogeneity. Now, let us discuss this dispersion in more detail. So, in order to start with this this interpretation, because heterogeneity, so that means your medium is like multiple degree of freedom system, MDOF system. MDOF system. So, I am going to write here about MDOF system. Like this, any MDOF system I have taken as like 5 degree of freedom system. Now, any MDOF, any surface wave propagation should satisfy three conditions. Which are, so what are these three conditions? First of all, satisfy equation of motion, second, should produce zero stress at free surface and zero displacement at infinite depth because of confinement. So, where there will be some stresses, but there will not be any displacement at infinite depth. So, it is causing some displacement at greater depth, but as you come near to the surface, because it is a free field condition, so stresses will be 0. Infinite depth, it will be significantly, I can call it, there will be increase in the stresses, and then of course, it should satisfy your this condition. So, if I consider here like 5 masses m1, m2, m3, m4, m5, if you go with this system, it is definitely indicating system having five degrees of freedom. I am just saying here like you can consider that equivalent to maybe different layers of soil, and at the center of that particular layer the mass is contained. So, I am just showing you because of any kind of excitation which may be because of wave propagation, how much displacement will be there. So, other physical properties of the system will remain same, but what we can understand here. So, possibly the system, because it is this, so possibly such system will have 5 degrees, 5 natural frequencies, yes, 5 natural frequencies corresponding to each mass, and it will be dominated, and that is how you will be having collectively 5 natural frequencies here. One will be corresponding to, while one frequency at fundamental mode, others will be at corresponding to higher modes. So, based on the stiffness and m1, m2 values, you can determine corresponding what will be the fundamental mode and what will be the higher mode values. Okay. So, if we consider each of these frequencies, each of such frequencies can be determined as omega n equals to twice omega naught sin n pi over 2 times n plus 1, where omega naught equals to root k by m, indication of fundamental mode frequencies. So, this you can call it as equation number 1, and same way maximum possible frequency, based on this maximum possible frequency omega n can be equals to twice omega naught. Now, if you consider corresponding to this, what is the wave number, if I call it as k as wave number. So, in general k n can be classified as twice pi n over L. This is called as equation number 2. So, from equation 1, it can be understood like omega n is not varying linearly with n. So, as more and more degree of freedom keeps on increasing, it is not varying linearly. The frequency corresponding to each, the natural frequency corresponding to each mode of vibration, it is not varying linearly. However, based on equation 2, the value of k n varies linearly with n. Okay, it is varying linearly with n, as we can see from equation number 2. Now, if we go here further, the propagation velocity of Rayleigh wave can be defined as Vr, which will be equal to omega n over k n, where omega n is angular frequency and this is your wave number. So, depending upon the ratio of omega n and k n, one can get to know what will be the Rayleigh wave velocity in the medium, particularly where k n is the wave number for the case of string, as we discussed in last slide, the string which is actually fixed at both ends. Now, same way in case of multi-layered system, if we consider considering the motion is also having different frequency content, as well as the medium, the subsurface medium is also multiple layer. So, this will be equals to K1, K2, K3, K4 different. So, each is resembling different portion of wavelength, and this is omega 1, omega 2, omega 3, omega 4, omega 5, omega 6 and so on. So, if you take particularly in case of dispersive medium subjected to wide range of frequencies, so how this wide range of frequency? By means of shock waves or shock, which you are actually generating by means of hammer impact. So, what will be the response of MDOF system? It can be like this. So, if you join these based on equation, we call it as equation number 3, one can understand how much will be the propagation velocity here of Rayleigh wave. So, consider for example, in case of 6 layer system or in case of 5 layer system, n equals to 5. So, your V5, that the Rayleigh wave velocity at layer 5 will be called as omega 5 over A5, which will be lesser than, as per figure, which will be V3 over V3, which is omega 3 over K3. Collectively, it's like depending upon the dispersive characteristics of the medium, dispersive characteristics of the medium, it may be possible like a higher frequency content, may travel at higher or maybe lower velocity. Both are possible depending upon the dispersive characteristic of the medium, or maybe lower velocity in comparison to lower frequency content. So, this content of lower and higher I am telling in terms of the frequency content of the shock wave. So, remember like the dispersive characteristic, dispersiveness is the characteristic of multiple degree of freedom system, that is more precisely you can call it as multiple layer system or subsoil stratification. So, as per Stokes, the Rayleigh wave disperses only when wavelength is 1 to 30 times the layer thickness. So, in this case only the Rayleigh wave which we are actually targeting to record, or we are trying to understand the dispersive characteristic of the Rayleigh wave, so that one can get to know what is the subsurface medium characteristics. So, this dispersive characteristic will be only shown when the wavelength is 1 to 30 times the layer thickness of the soil. So, that is how you can get an idea like what will be the layer thickness, and corresponding to that what frequency content or what wavelength is going to undergo any kind of dispersion, particularly analyzing the Rayleigh wave velocity. So, because I discussed about dispersive characteristic, which is shown here, dispersive characteristic shown above is in case of heterogeneous, like MDOF system, and in this case we are interested, particularly when we go for subsurface exploration, this MDOF system is, you can consider as multiple layers of soil. So, that is you are interested to find out based on the dispersive characteristics. Now, we will see how this dispersive characteristics changes with respect to the depth. So, if I put it here, amplitude at depth z to amplitude at surface. Again, this is causing two kinds of motions, one may be vertical component, one will be horizontal component. So, I am going to give you here, this is like 0.0, 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, and same way here also you can have 0.2, 0.4, 0.6, 0.8, 0.2, 0.4, 0.6, this is like minus 0.8. So, this is like again. So, with 1 if I start, again on this side you will be having 0, 0.2, 0.4, 0.6, 0.8, 1.0, 1.2. It is not on scale, so be careful with that part. Again, so start, it is showing, it is going to give you with respect to depth for different Poisson's ratio material how it should be different here, it should be like this. So, this is about vertical component of wave. And this is z over lambda r, that is wavelength. If you are making in comparison with respect to the depth, this will be like minus 0.4. So, this is for horizontal component, it should be like this. This is like horizontal component of now. This is varying because of change in your Poisson ratio. This is for Poisson ratio of 0.5. This is for new Poisson's ratio of 0.4, this is for nu equals to 0.25. Similarly, here also this will be corresponding to 0.25, 0.33, 0.4, 0.5. One important observation to be drawn here, it is like if you consider a particular wavelength or particular wave, as you are going deeper, that is as you are going as the z value increases, that z is like depth from ground surface. So, if you are interested to if you target for one particular depth and try for different wavelength. So, as the wavelength keeps on increasing, the value keeps on decreasing. So, that means you can say like with increase in wavelength, that is you are going towards this like there will be increase in z by lambda r value, the amplitude of wave will increase at same depth. On the contrary, if you target keeping z constant, second thing, keeping lambda r as constant, like for a particular kind of particular wavelength. If you are observing that with respect to the depth, you will see the amplitude of wave decreases with depth, with increase in depth. So, that is how Rayleigh wave velocity, though the amplitude is significant at the ground surface, but as you go deeper and deeper, the signature of Rayleigh wave to be detected by any sensor, it will be relatively less. So, amplitude of wave decreases with increase in the depth. This is same way it is applicable for. So, this is indicating. So, this is so one I discussed about the dispersive characteristics. Second, here I am trying to show how the amplitude of the wave, because finally your detection of the wave, secondly your signal to noise ratio will be governed by the amplitude of the wave. As you can see from this figure, the amplitude of the wave. So, this is like at any depth, if you put how much the amplitude is going to increase or decrease with respect to the amplitude at the surface. So, this is a ratio like this. So, whenever it is reaching 1, it means at that particular depth the amplitude is almost equivalent to the amplitude which was recorded at the surface. Now, another important thing, so we discuss about what is dispersion, and then we discussed about change in amplitude with depth, amplitude with depth, remember dispersion is a characteristic of heterogeneous medium considering Rayleigh wave. So, whenever I am telling dispersive characteristic in case of heterogeneous medium, I mean for Rayleigh wave. So, this is about the background. So, when we go for surface wave analysis, what are the advantages? Yes, advantage also we had discussed, advantages of using surface waves in interpreting near surface medium. So, we started with this, then we went to what is the characteristic of the wave in heterogeneous medium, and then what will happen if you observe the, if you try to record the wave at different depths, what will happen there. Now, two methods precisely, the objective of introducing this to this course, this topic to this course, like more commonly in like forensic investigation, in microzonation studies, even in quality control also, when I discuss about the advantages, the surface wave based geophysical methods are becoming more and more common. So, one is like MSW survey, that is multiple channel analysis, multi-channel analysis of surface waves, and the other one is like SASW, that is like spectral analysis of surface waves. So, in this, the first one, we try to find out the dispersive characteristic over multiple frequencies or multiple channels using multiple number of geophones or sensors. That is how you will be able to identify at the same time, based on your signal to noise ratio, which is the fundamental mode based dispersion curve from your field record and what are dispersion curve and dispersion curves at higher modes. In spectral analysis of surface wave, we try to understand the dispersive characteristics are addressed using a pair of geophones That is how you will go for multiple recordings with varying geophone interval, with varying geophone distance. This will help. So, the identification of fundamental and higher mode, will not be possible or will be difficult based on one record, and hence multiple recordings are mandatory. So, this is like there can be more number of discussions based on MSW survey, based on your SSW survey, but this is like more precisely in multi-channel analysis. We put number of geophones and we try to find out the dispersive characteristics over wide range of frequencies. That will help you once you see these dispersive characteristics in terms of signal to noise ratio, also in terms of in terms of signal to noise ratio, that will help you in identifying which is the fundamental mode, which is the higher modes. And second one is spectral analysis of surface waves. We go for this interpretation in terms of two frequencies. Okay, one important and last parameter here is the entire test consists of field recording, that is based on geophones you will put and try to record. So, shock waves recording, then dispersion curve from field record, and the last part is determination of shear wave velocity profile or Rayleigh wave velocity profile based on inversion. It is called as inversion because you try to approximate or you try to find out based on, you take an initial earth model and based on this model find out theoretical dispersion curve, try to match with experimental dispersion curve obtained in part 2, and then if it is not matching, then update your theoretical dispersion curve and then compare with your experimental dispersion curve. So, unless based on your R square value also you can get. So, it is like every time you keep on updating your theoretical dispersion curve till it matches with your experimental dispersion curve, and once both are matching, corresponding to theoretical dispersion curve obtained at the last of the iteration, you will get your shear wave velocity profile, that is with respect to depth, shear wave velocity variation with the depth that will identify stratification details. So, this is more I try to give here and then overall idea about what is the surface wave method, what are the advantage when we go for surface wave method in comparison to body waves. Then overall what is the characteristic based on which a surface wave see heterogeneity in the medium. If that characteristic, that is called as dispersion characteristics or dispersive characteristics, if based on any method we are able to identify that dispersive characteristics, based on field record we will be able to find out equivalent to that field based dispersive characteristic, what are the stratification in the tails. Okay. So, that is all for today. Thank you so much.